I do this, if I integrate f k of x dx from 0 to, let's just pick a very big number at the moment, much greater than 2 to the k. Right? If m is 2 to the k, that's beyond, in other words, all these turn to 0 at m. For all k, that's going to be 1, right? What's the limit, the pointwise limit, as n goes to infinity of fn of x? Oh, what are they doing? Yeah, this one's 1, that's a half, that's a fourth. What's happening to you? 0. So, the limit as n goes to infinity of 0, 2 to the n, f sub n of x dx is 1. But the integral from 0 to 2n of the limit as n goes to infinity of fn of x is 0. So if you take the limit first, you get nothing but zeros. Doesn't matter how far you want to integrate, you get 0. If you integrate first, you always get 1. And then it doesn't matter how far you go, you always get 1. Right? So here's a case where you cannot commute the limit operation and the integration. It is extraordinarily convenient to be able to do that in certain circumstances. And the Lebesgue integral is much friendlier for doing that. We'll prove some theorems about Lebesgue integrals that give you the conditions where the limit of the integral is the integral of the limit. That's extremely convenient. But in the Riemann situation, this sort of thing can happen. Okay? All right. Now we gotta take a deep breath and go through a little bit of background, just even to define the Lebesgue integral. Okay, a measure space. What does that even mean? It means there's going to be some kind of space where there's a notion of length or area or volume defined on it. That's what it really is. Formally, it's a triple. It's a ground space, the set of all points. And capital sigma is a collection of sets in that ground space, right, that behave very well with one another. I'll explain how they behave in a second. But it's a distinguished collection of subsets of X. And mu is a notion of length, or generally it's called measure. You can think of it. So sets in X may or may not belong to the family sigma, but if they do belong to the family sigma, then you can apply mu to them, and you get a number out that is the length of that set, the measure of that set. In this case, we're restricting the measures to being non-negative real numbers. It could be infinity. So you could have the measure of the real line is infinite. The measure of the line from 0 to 1 is 1, right? The measure of the line from -2 plus 5 is 7, and so forth. Right? All right. The thing sigma is, this was philosophically a tough point for the people around the turn of the last century. They wanted you to be able to have the length of any set. If you have a ground space X, it seems like, well, we should have
sets that have, every set should have a length, right? Every set of real numbers should have a notion. The weird thing is, that's highly not true. There are sets for which it is impossible to define a length. I'll show you one of those maybe Thursday. There are sets lurking around that have no length. They're pathological. It's not the sort of thing you run into with a measuring tape. They're constructions which are explicitly designed to be not handled by the measure, right? Suffice it to say, the power set, which consists of all subsets of X, generally is not sigma, which consists of those measurable sets that play well together. What's that mean? They form a thing called a sigma algebra. An algebra of sets does this. It contains the whole space X. It contains arbitrary unions. So if you have an arbitrary union of sets that are in sigma, that thing is back in sigma. It contains complements. So if a set is in sigma, its complement relative to X is back in sigma. That's just an algebra. A sigma algebra is something a little better. It's an algebra which has this property as well. Any countable union. The countable union is back in the sigma algebra. In the other case, just a union is in. Here, a countable union is back in. Wait a minute. I remember this. The mnemonic is cut. Algebra. It's complements, unions, the total set. You have trouble remembering this. So an algebra of sets has those three features. And then a sigma algebra has things like this. The union I equals 1 to infinity. Some subset AI is back in the sigma algebra. Generally, that's not true if you take an infinite union, right? But in a sigma algebra, that's true. With De Morgan's laws, you can establish this. This might be a good exercise. You can show that the infinite intersection are countable. Remember, these are countable, not arbitrarily infinite. Countable. That's what the sigma always means in these contexts. Sigma finite, sigma algebra, right? Sigma this, sigma that. It means countable somethings, usually a union. Okay. Did you? Okay. Well, that's good. So we have a sigma algebra of measurable sets. The notion of measure here, and the ground space X. All right. We have all those things in place. Now, there's a huge theory of measure which you can read about. It's an interesting subject. We started to do a little bit of that last summer in Algebra 1, or in Analysis 1. Remember that? Proved a few things. Does anybody remember that?
Yeah.
A little bit. Okay. This is the notion of a measurable function. If you have a function from a measure space,
switch back.
a measure space to a topological space, you say that the function is measurable if the pre-image of an open set is a measurable set. So what you demand is that the pre-image of an open set is measurable. So if U is in the topology, it's an open set. You take its pre-image, everything in the measure space that was mapped into U, the open set, and you look and see, geez, is that in the sigma algebra or not? And a measurable function has that property always. That's the definition of measurable function. It's from a measure space to a topological space, and the pre-image of an open set is virtual. And you can show that then the pre-image of a closed set is virtual, the pre-image of a half-open set is virtual. By the way, how would you do that? Let me just, how do you write